Yesterday, where exactly we stopped on? I think at those equations like resistance, uh, resistivity, in terms of relaxation time. Am I right? Yes, yes, yes. So, here from yesterday's concept, finally we found R equals to like rho L upon E, first equation, and rho is equals to, anyone remember, Nana? M by like N E square tau, correct? Rho resistivity, Srinivitya. Is it correct? NEVD. Uh, I think L you missed, Nana, there in your equation, what you have posted. Okay, anyhow, is it correct? M by N E square tau? Yes, okay, good, good, good. Means from the two equations, what I'm trying to say today is here resistivity depends on what factors and resistance depends on what factors. Okay, here if you see, number one, rho is inversely proportional to the number of electrons per unit volume, N, and the relaxation time. Whereas E is charge on electron, M is mass of electron, they are obviously constants. Okay, we won't consider. But here N is also a constant, sir. Why you are considering here that N? If you ask, N is number of electrons per unit volume, but problem is per unit volume the number of electrons is different for different materials. Now what I am saying, if material is changed, resistivity is changed. That's why depending factors, if you write, that implies the depending factors. Factors here, if we write, okay. Number one, what we write, rho is inversely proportional to N. But N is different for different materials, means depends on nature of material. If material is changed, resistivity will be changed. For different materials, resistivity will be different. Okay. And number two, here tau, relaxation time. Relaxation time, I think yesterday we have discussed. When temperature is increased, relaxation time decreases or increases, decreases, exactly what I have posted, correct, decreases. So when temperature is increased, relaxation time decreases, means resistivity increases. I think yesterday we end with this point only. Okay. Yes. So number two, it depends upon the temperature. Okay, when temperature is changed, relaxation time changes, accordingly resistivity changes. These are the depending factors of which are influencing the resistivity of a material. Okay, but here in the same way, if you come to the resistance, here resistivity, again if you substitute M by N E square tau here, again R is also depending upon N, depending upon relaxation time, in addition depending upon length and area of cross section. So here problem is R, I have to write, is directly proportional to, of course inversely proportional to N tau as usual. That depends on, they are depending factors of rho. And here additionally you are getting L by A. That's why here resistance depends on ohm. If you want to write here, depends on number one. Here we write as usual the nature of material, and number two temperature. Additionally we are taking number three length, and fourth here we are taking area of cross section. Okay, these are the factors influencing the resistance. Okay, of course here first what we have to discuss how the resistance or resistivity depends on temperature. Why? Because nature of material, if material is changed, resistance or and resistivity both will be changed. So for different materials we say the resistance or resistivity is different. Okay, those values we have to find out practically. That is a different story. Okay, based on what relaxation time and nature of and the number of electrons per unit volume. Okay, but here how it depends on temperature we have to find out. Okay, before finding out, first of all here we try to find out one example here. How to find the resistivity from the number of electrons per unit volume. Okay, suppose I take one material. Okay, it is a conductor which a conductor has suppose 10 power 23 atoms, okay, in a volume of like some 100 centimeters cube. Okay, what has given, and each atom releases one electron, okay, in the excited state. And here indirectly you can find out what, Nana? The number of electrons are there and the volume is there. 10 to the power of 23 atoms means you will get 10 to the power of 23 electrons. Why? Because each atom releases one electron. There are 10 power 23 electrons in 100 centimeter cube. Means number of electrons per unit volume you can calculate. That is N you can calculate. Okay. Mass of electron, charge on electron, you know. Right? Then here the resistivity rho of material, this is given to you, is say some 10 into 10 power minus 8. Of course, we forgot in writing the unit of resistivity. From here you can write what unit of resistivity is, what might be unit of resistivity, Nana? RA divided by L. R is ohm, area is into area is meter square divided by L, that is M. So what the unit you are getting? Ohm into meter. 1 M get cancelled. This is the unit now. Okay. Now here 10 into 10 power minus 8 ohm meter. Find. ఇక మీకు అర్థమైంటుంది వాట్ ఐఎమ్ గోయింగ్ టు ఆస్క్. ద రిలాక్సేషన్ టైం. Okay. Will you calculate this one, Nana? Just by substituting the values here. Simple solution. Number of electrons per unit volume we are trying to calculate. Number of electrons, capital N, per unit volume. Okay. That is N is 10 power 23. Each atom is producing 1 electron. By volume is 100 centimeter cube. Means we need some calculation here. 10 power minus 6 meter cube. Converted into meter cube. So how much you are getting there? Altogether 10 power minus 4. That is 10 power 27 electrons. Okay. Rho already given 10 into 10 power minus 8 means after multiplying you will get 10 power minus 7 ohm meter. Next, what has given? Nothing. Just he is asking tau equals, but we know. Okay. What we know? Mass and charge on electron. E is equals to 1.6 into 10 power minus 19. Mass is 9.1 into 10 to the power of minus 31 kg. I think all of you remember. Approximately you can take it as 9. And E is 10.1.6 into 10 to the power minus 19 coulombs. Okay, it is now your turn. How much is the value of tau that you have to tell after doing some calculation? Will anyone try here using your calculator? Anyone got the answer? Rho n e square. Sorry, m by rho n e square. 3.5 into 10 to the power of minus 20. You get there, Nana? Shura? Is it 10 power minus 10? Anirudh is saying it is 3.5 into 10 to the power of minus 20. Shall I conclude it is the answer? Still many are doing, I think. Is it correct, Nana? Interact today, no one is responding. Mine 10 power plus 8 in Nana, Srinidhi Priya. Oh, I think all others are just attended the class and not there at the screen, I think. They are enjoying there at the. Oh, I enter calculation, different students are giving different answers. Shrama. One is saying 10 power 18, other is saying 10 power 15. One is saying 10 power minus 20. Oh my god. So simply you are leaving it to me only again. 9 into 10 power minus 31 upon, this is rho. Rho is 10 power minus 7. 1.6 into 10 power minus 38 into 1.6. 19 twos are 38. N is 10 power 27. 27 minus 7, 20. 20 means 18. Minus 18. Minus 18 taken to the numerator, plus 18. Minus 31 plus 18. This is minus 13. 9 by 2.56, approximately 3. 3 point something into 10 to the power minus 13 కదా నాన్న. నేను చెప్పాక ఆన్సర్ చెప్పడం ఏందిరా ఎస్ అనేసి ఎంతసేపు ఏం చేశారు బడుదాయిస్. ఇట్లయితే ఎట్లా నేను చెప్పాక ఆన్సర్ చెప్తారేంట్రా. 10 power minus 13 ఆర్ సంథింగ్. సూపర్ రా, ఏం క్యాలిక్యులేషన్స్ రా మీరు, సరిపోయారు. 3.5 into 10 to the power of minus 13 seconds. This is the relaxation time what we got. Okay, good. Right here, in this way we have to solve the numericals related to rho nana, and it is nothing, no twist is there nana in this kind of problems. Direct we have to substitute the given values. Just where he give a bit twist, how many number of atoms are there, okay, and each atom is producing how many number of electrons. By that we have to find out just n value. Rest of the things they give and we have to find out. Okay, this is one model. And then if we come to here, specifically how it depends upon, means first model we have done there, how it depends on nature of material. Next we are coming to temperature. Okay, temperature here, what they say, what we have found, when temperature is increased, then we know rho and of course r both will change, both are increased. So what can we say here? They are looking like when temperature is increased, resistivity and resistance both are increased, means what it is, they are looking like, once you observe the expansions of materials nana, by the increase of temperature, length increases, area increases, volume increases, like, and it is just like your thermal properties of matter first year. Okay, there we say linear coefficient of expansion, areal coefficient of expansion, volume coefficient of expansion, alpha, beta, gamma. In the same way here we have to say temperature coefficient of resistance or temperature coefficient of resistivity. Okay, So here first, how the temperature changes the resistivity. If you see, same kind of derivation, okay, no change at all. But the thing is, initial temperature we are taking 0 degrees Celsius. Okay. So at 0 degrees Celsius, that is T1 degrees Celsius, the resistivity rho is equals to rho 1. Resistivity equals to rho 1. And at T degrees Celsius, means when temperature is increased to T2 degrees Celsius, the resistivity becomes rho 2. Okay, for convenience, what we are taking this rho 1, okay, we are taking it as rho naught, rho at 0 degrees Celsius, and this rho 2 at T2 degrees Celsius, we are taking rho at T degrees Celsius, rho suffix T. Okay. Then how you derived the linear coefficient of expansion, like a change in length is proportional to initial length, is proportional to change in temperature. So in the same way, change in resistivity rho T minus rho naught is proportional to initial resistivity proportional to change in temperature T minus 0. Okay, and you are getting rho T minus rho naught is proportional to rho naught into T altogether. Now you are replacing the proportionality with some constant, representing here also with the letter alpha. Alpha rho naught T is equals to rho T minus rho naught. And I am getting that implies one equation, rho at T degrees Celsius equals to how much? Then by taking this one to the other hand, I will get rho naught times what? By taking rho naught common, 1 plus alpha T. One equation. The same thing I can write here. How rho naught into T taken to the other hand, I am writing alpha equals to how much? Alpha is equals to, I am going to write rho T minus rho naught upon rho naught times T. These are the two equations usually we use in numericals. Okay. The other one is alpha is equals to like this. Wait, these two equations we use. Right? And here alpha is what? We have to say who is alpha. Where alpha is the temperature coefficient of what? Resistivity. Okay. This is one equation, Ra. And the same equation for small changes of temperature. They're from 0 degrees Celsius to like 10 degrees Celsius, 20 degrees Celsius. Not like temperature is increased by 100 degrees Celsius, 200 degrees Celsius. You can increase now. Why? Because melting point of iron is 500 degrees Celsius, all of you know. So you can raise up to 500 degrees Celsius before melting. So that is your wish. So we can raise the temperatures even 100 degrees, hundreds in hundreds, or in tens, or in multiples of 1. 1, 2, 3, 4, 5 degrees Celsius like. So usually for small changes of temperature, we can use the differential form for small changes of temperature. We write here alpha is equals to what? Rho T minus rho naught means differential form d rho upon Rho naught means initial rho into T is actually T minus 0. That is change in temperature now. Okay. So this is dt. We can write like this. This is differential form. Okay. Or cross multiplication d rho equals to, we can write rho alpha into dt. Okay. This is the equation in differential form. So any equation you use when you come to numericals, depending upon the question. Okay. And here, if they ask what is the unit of alpha, you can say unit of alpha is, predict what is the unit of alpha. What might be the unit? Rho at the numerator, denominator rho means, yes, Srinidhi Priya, correct. Rho t minus rho naught unit ohm meter, rho naught unit ohm meter. So ohm meter get cancelled. Only temperature unit you will get in the denominator per degree Celsius. This will be the unit. And that too, it is change in temperature. Change in temperature in first year, you know, 1 degree change in temperature is equals 1 degree Celsius is equals to 1 Kelvin during the change of temperature. That's why we can say the same alpha even in SI system also, that is per Kelvin. Either per degree Celsius or per Kelvin you can use. In both the units you will get the same value. Why? Because it is change in temperature. Okay. So here alpha remains the same in both SI and CGS units. In CGS and SI units. SI systems. Okay. This is the story now, what we have understood. Here you have to raise one question. What? Sir Marie, the formula you derived by taking the initial temperature 0 degrees Celsius, sir. But if I don't take the initial temperature 0 degrees Celsius, if I want to increase the temperature from 25 to 225, okay? So initial temperature is not 0 degrees Celsius. If the initial temperature is not 0 degrees Celsius, shall I use the same equation there, sir? Like rho 2 minus rho 1 upon rho 1 into T2 minus T1, shall I use? Then I say no. Okay. So in next page, what I am going to write? If the initial temperature is not 0 degrees Celsius or 0 Kelvin, anything, 0 degrees Celsius, then the formula like rho t means rho 2 minus rho naught means rho 1 upon rho naught means rho 1 into t. T is delta t, T2 minus T1. Shall I write that equation like this? This is what you ask. Okay. Then we can use this equation for small changes of temperature. That's why I wrote the same equation you observed there in the previous page. ఒకసారి observe చేయండి నాన్న. You can observe there. This rho t minus rho naught, I accepted as rho 2 minus rho 1. I wrote it as d rho. Observe here. By rho naught, I took it as rho, means rho at initial temperature. Into T minus 0, directly I took it as dt. And I gave this equation. But already I wrote the condition here. Observe? Okay. So same d rho is rho 2 minus rho 1 by rho 1 into T2 minus T1 is applicable for small changes. Okay. అంటే ఇది ఎలా ఉంటుందంటే నాన్న ఫైండింగ్ అవుట్ ద ఎర్రర్స్ అండ్ అప్రాక్సిమేషన్స్. సపోజ్ z ఈక్వల్స్ టు x divided by y. What is the error in z? Generally what we do, apply log and differentiate. That method is valid for small errors. Can if the errors are like x, error in the x is 100%, error in the y is 300%, but we should not use that formula. We have to differentiate by u by v method and divide with the z. Correct, Anana? Okay, you should not apply log and differentiate. ఇదే మనము like resistors 1 by r equals to 1 by r1 plus 1 by r2. What is the percentage change in resistance చేస్తున్నాం in first year? Did you remember? In units and measurements chapter, we did not apply log and differentiated this equation. Yes, log apply చేసి differentiate చేయలేదు, directly differentiated and divided, got dr by r. Okay, so if the small changes are there, we can use, and approximately you will get the same value. That's what he is saying. And for small changes, you won't get much difference in the resistivity values. Okay, then again we ask, why we are not getting much difference in the resistivity values? And you are saying that rho 2 minus rho 1, is it small, sir? Yes, that's what I am saying. Why? Because resistivity is in the order of, as a resistivity for different materials, if you see practically, rho is in the order of 10 power minus 8 లో ఉంటుంది నాన్న. అందుకే you observe there one question what I have given there. How much I give the resistivity here? 10 power minus 8. 10 something into 10 power minus 8. And its order is 10 power minus 8. Okay. Mari sir, after substituting the value of alpha, sir, value of alpha is in the order of 10 power minus 4. Okay. So ikkadiki vaste here I say the order of alpha, that is 10 power minus 4. Okay. So I am writing here alpha is in the order of 10 power minus 4. And then look at the values what we are taking, rho 2, rho 1, rho 1 alpha 10 power minus 4. All these values, they are very small. And again, for small changes of temperature, you won't find much difference in the final answers. So you will get the approximate values. If the change in temperature is like 100 degrees Celsius, 200 degrees Celsius, you are multiplying with 2 zeros and 3 here, with big values like 2 and 3. 200, 300. Okay. If you multiply 2 decimals variation వచ్చేస్తుంది నాన్న, point will be shifted by 2 decimals. Okay. Appudu this formula is not applicable. So when you come to numericals, don't use this formula for all changes of temperature. Condition is very important for small changes of temperature. But for big changes, and what you said like 200, 300 degrees Celsius, what we have to do, sir? You have to find out what rho 2, rho 1 separately. Why? Because derivation is saying that you have to take initial temperature at 0 degrees Celsius. So by considering, we don't know at 0 degrees Celsius at what is the resistivity. That's why first what has given rho 1 to you. Okay, rho 1 I write like according to the formula rho naught into 1 plus alpha t. alpha t, t1 minus 0, that is t1. In the same way, rho 2, again I start with rho naught, exactly, Srinidhi Priya. Rho naught into 1 plus, here also alpha into t2 minus, initial I took it as 0, alpha t2 minus 0, t2. Divide these two equations to eliminate rho naught. Why? Because rho naught is not given, rho 1, rho 2 are given. So simple. And that implies you are getting rho 1 divided by rho 2 is, is equals to 1 plus alpha t1 divided by 1 plus alpha t2. Okay, cross multiplying and rearranging the equations, finally you will get what alpha is equals to, cross multiply చేసి కాస్త terms and rearrange చేస్తే you will get rho 2 minus rho 1 divided by rho 1 t2 minus rho 1 rho 2 t1. Okay, by simplifying the above equation. So either you can remember the equation like alpha is equals to rho 2 minus rho 1 by rho 1 t2 minus rho 2 t1, or you can remember even like this, rho 1 by rho 2 is equals to 1 plus alpha t1 divided by 1 plus alpha t. Okay, any form you can remember for the numericals. And me ఇష్టం. Now you check here, rho 2 minus rho 1, you can write it as a d rho at the numerator. But denominator you can't write like, you can't take rho 1 common to write rho into dt. ఇప్పుడు నా పెయిన్ మీకు అర్థమైందా? d rho by rho into dt. ఇది కరెక్ట్ అన్న డినామినేటర్. Rho 1 you can't take common kada. That's why you can't write it as t2 minus t1 dt here. Yes, అందుకని this is not equal to d rho by rho into dt at high temperatures. లేదు, ఇలా రాద్దాం, ఫర్ లార్జ్ చేంజెస్ ఆఫ్ టెంపరేచర్. ఓకే, అంటే బిగ్ అంటే బాగుండదేమో, మరి లార్జ్ చేంజెస్ ఆఫ్ టెంపరేచర్స్. ఏ changes of temperatures. Okay, so this is what I said. Andukani already I said there, only for small changes of temperature alpha can be written as d rho by rho, differential form d rho by rho into dt. Okay, and here according to the theory already you concluded, watch, when the temperature is increased, the relaxation time decreases, resistivity increases. And all the times rho t is greater than rho naught. Okay, so according to theory you can write, we write here as we know, what we know, బయట వర్షం పడుతుందని కాదు మనకు తెలిసింది, what we know, rho t is greater than rho naught, and when temperature is increased resistivity increases, or rho 2 is greater than rho 1. And he values, if you substitute here, numerator you will get positive, denominator also you will get positive. Okay, positive by positive you will get alpha positive. Thus we can say alpha is not negative, is positive. So this is, we derived actually the formula and everything we are deriving for whom, Nana? For conductors or insulators or for other type of materials? Only for conductors kada? Only for conductors, correct Andrew? Okay, so alpha we got finally positive for conductors. But what about insulators, sir? Insulators, we won't say alpha. Why? Because their resistance, అసలు వాటికి ఉండటమే చాలా హై రెసిస్టెన్స్ దే హ్యావ్. ఓకే, అందుకే కరెంట్ ఆల్మోస్ట్ జీరో త్రూ ద ఇన్సులేటర్స్. Their changes are negligible and alpha is almost zero for insulators and a very small alpha you will get for insulators. That's why we won't discuss about the alpha for insulators. Okay, apart from these conductors and insulators, I think you know we have few more materials. Inka కొన్ని ఉన్నాయి నాన్న. Do you know them? Who are they apart from conductors and insulators? Superconductors. Not superconductors. Yes. Srivasa, yeah, semiconductors. Superconductors అంటే the conductors only behave as superconductors. Superconductors అంటే the resistance becomes zero at low temperatures. And a simple logic. If temperature is increased, resistivity increases, and when temperature is decreased, resistivity decreases. That almost tends to zero. Where at very low temperatures like 4 Kelvin, not 4 degrees Celsius, 4 Kelvin, 5 Kelvin, 3 Kelvin, like, and almost close to 0 Kelvin. That time they behave as superconductors. Okay. సరే, మీరు అన్నారు కాబట్టి we write here who are superconductors. Superconductors are nothing but conductors. Okay, but here in the same way, alpha is positive and the temperature is increased, resistivity increases. Temperature decreases, resistivity decreases. Okay, as the temperature decreases, we write the resistivity decreases and the rho decreases, and nearly equal to zero at very low temperatures. At the temperatures close to not 0 degrees Celsius, close to 0 Kelvin. Okay, not okay roy, that is మీరు సూపర్, దీన్ని ఓకే అనుకో అక్కడ. దిస్ ఇస్ 0 Kelvin. Better I write 0 Kelvin. Okay, that time when the resistivity is 0, then the conductors are called as superconductors. When rho is approximately equal to 0, then the same conductors, not other type of material, same conductors, and a copper wire behaves as superconductor. Copper is a conductor. Okay, in the same. Then the conductors behave as superconductors. ఇవి కాకుండా we have another type of materials. They are what Srivasa told, semiconductors. Okay, for semiconductors we say alpha is negative. It is very important. Alpha is negative for whom? Semiconductors. Okay, alpha is negative, and what does it mean, sir? That is, with the increase of temperature, what happens, Nana? The resistivity decreases. resistivity decreases. Okay, and the resistance decreases with the increase of temperature. Okay, ఇది temperature dependence నాన్న, right? ఇప్పుడు related to these kind of temperature dependence, okay, just you try to solve a few questions here. 1 minute. No, it's not there. I will show 1 or 2 questions there related to it so that you can practice them. Yes. Now I am going to share one small assignment, Rana. You see there so that you can solve them. Here, I think no. Yes. Here, look at the resistance type of model, Nana. Okay. Look at this 17th question. The resistance of a conductor. Are you able to see this question, Nana? All of you. Whatever I have shared. Able to see? Very good. What I am saying, look at the question number 17. Okay. The resistance of a conductor is given as R equals to R naught into 1 plus AT plus BT square plus CT cube. And how the resistance changes with the temperature, he gives some relation. A, B, C are positive constants. R naught is the temperature at 0 degrees. Happy. Very good. T is the temperature in degrees Celsius. The values of A and B, C are given. Temperature coefficient of resistance at 100 degrees Celsius and alpha. Okay. Right. Mari here it is given as a variable varying with the temperature now. Varying with the temperature and there is no option for us. What we have to do with what? Differential method only. Okay. So first of all, what we have to do? dr by dt, differentiate with respect to temperature. I think all of you following there. Okay. By differentiating, first you copy the question, Anna. Why? Because it is not there on the whiteboard. Later you won't find this question. All of you copied the question, Anna? Shall I start? Yes. dr by dt equals to, by differentiating, you will get r naught times differentiate 0 at, that is a, bt square, that is 2bt, and ct cube is 3t square. Okay, this is dr by dt. So dr by dt also I am getting a big value here. right? And here, what is our formula for alpha? Alpha is equals to dr divided by r into dt. Who is r, Nana? 3ct square. Oh, I forgot c there. Okay, okay. This is 3ct square. Sorry. Good. Then here, anything I missing, Nana? A plus 2bt plus 3ct square. Correct only. Dr by r into dt. Where r is what? Resistance at 0 degrees Celsius. Okay. Where R is resistance at 0. At 0 degrees Celsius, you T equals to 0 here in this equation. You will get just R equals to R naught kadanana. Am I right? If I put T equals to 0. Yes. R equals to R naught in this equation. If I put T equals to 0. So initial temperature he has given here, it is 0 degrees Celsius. So put T equals to 0, you will get R equals to R naught. Inka అయిపోయింది నాన్న. Alpha is equals to, you will get what? dr by dt means R naught into A plus 2bt plus 3ct square divided by, this is dr by dt, divided by R is R naught, and R naught is unnecessary data. That's why he did not give the value of R naught in the question. But what are required? A, B, C values. That's why he gave A, B, C values here. Okay. Now you can substitute and find out the value. A is 2 into 10 power minus 2. 2bt, 2b, 4 into 10 power minus 4 into 100. That is 4 into 10 power minus 2 plus square. Okay. 3c, 3 2s are 6. 6 into 10 power minus 2. Okay. Correct, Nana? Is it right? ఎరా ఏంద్రా ఎవరు రెస్పాండ్ అవ్వట్లేదు. ఏంది ఈరోజు క్లాస్ బాగా డల్గా ఉంది. ఆల్ ఆఫ్ యూ దేర్ ఇన్ ఫ్రంట్ ఆఫ్ స్క్రీన్ రా. స్క్రీన్ ముందు ఉన్నారా మీరంతా? ఎస్ అమ్మయ్య. స్క్రీన్ ముందైతే ఉంటారు, ఆన్సర్ మాత్రం చెప్పరు. ఎస్ సార్, కరెక్ట్. ఓకే. And this is equals to how much you are getting, Nana? 0.12. This is 0.12. Right? Good. Idi Nana, per degree Celsius. He already said, find the temperature coefficient of resistance in per degree Celsius. Okay? Pradhamina, how to solve the questions? ఇంకోటి ఏమైనా ట్రై చేస్తారా? చూద్దాం. ఇఫ్ దొరికితే we will try. Yes. So we will try to search for another question. Where are the temperature coefficient problems? అంతేనా? దట్స్ ఆల్. అరే లుక్ ఎట్ దిస్ వన్ అని ఇదేదో. ఎస్ ఎస్ ఎస్. అంటే ఇది అవ్వాలి అంటే ఐ థింక్ వీ హ్యావ్ టు సాల్వ్ సిరీస్ మోడల్. అవ్వలేదు. రైట్, గుడ్, నో ప్రాబ్లం. మీరు ఏమైనా చేయగలుగుతాను అంటే ట్రై దిస్ క్వశ్చన్ 14th. అంటే లైక్ టేక్ ఇట్ యాజ్ హోంవర్క్ అండ్ ట్రై ఇట్. ఇది కూడా టెంపరేచర్ కోఎఫిషియంట్ మోడలే. ఐ థింక్ యూ కెన్ సాల్వ్ ఇట్. చేయగలరు అనుకుంటున్నాను. కానీ ఇది ఐ థింక్ నాట్ రిలేటెడ్ టు దిస్ ఆల్ఫా. ఆల్ఫాకి రిలేటెడ్ కాదు. ఐ రైట్? ఎనీవన్ రెడ్ ద క్వశ్చన్? చదివారా నన్ను ఎవరైనా? నాట్ రిలేటెడ్ టు ఆల్ఫా. ఇదంతా కూడాను రిలేటెడ్ టు ఎంఎస్ డెల్టా టీలోకి వెళ్ళిపోతుంది. థర్మోడైనమిక్స్. dq is equals to ms dt. ఆ మోడల్లోకి వెళ్తాం. సరే, ఇఫ్ ఇట్ ఈస్ పాసిబుల్ ట్రై టు సాల్వ్ ఇట్. ఓకే, unluckily we have only one question here related to alpha model in this assignment. Right, again we are moving back to white screen. Shall I move to white screen now? Shall I move? Yes, Shashank. Right. I'm going to white screen now. Yes, okay. Right, going to white screen here. After coming back to whiteboard, solving few questions there. Here, no, not like that. R is inversely proportional. Don't say like inversely proportional to temperature. Here, by the increase of temperature, the resistance decreases not according to this concept, Nana, and RVS Anirudh. Why? Because for semiconductors, the explanation of conductivity, we won't use the flow of electrons. That is completely a different story. Okay? And we won't use even this formula to find out the resistivity and all. It is applicable for whom? If there are surplus of free electrons, then we can use this concept. As the explanation is completely different. That's why there, and we have a separate chapter, semiconductors. There we will discuss, no problem, how the resistance changes with temperature, why the resistance decreases with the increase of temperature. Okay, why the opposition? Resistance means opposition for the flow of electrons decreases. Right? Right, good. Then just I give some idea. The explanation we will get there in that chapter. Here, sometimes we require this temperature dependent resistances. Okay, temperature dependent resistances means, like suppose I want one electric heater. Okay, iron box, geyser, okay, electric stove. In such type of electrical devices, there I require, by turning on the switch, by passing the current, I require more amount of heat. Heat means more opposition for the flow of electrons required. More opposition means more resistance is required. More resistance means by the increase of temperature, the resistance should be increased quickly, not slowly. Okay. So for such type of materials, okay, what you use? So first of all, basically how you prepare the lab resistors, how you prepare the heating elements. Okay, lab resistors means in the lab while doing an experiment, we connect one resistor, okay, and pass the current for a long time. While doing the experiment, the resistance of the wire or the resistance of resistor should not be changed. And the temperature almost independent of temperature we require. And for the resistance, changes in resistance values must be negligible there. And for lab resistors, what I am saying, alpha should be negligible and very small. That is very small we require. Mari that much small, who will have, sir? Naturally, the elements won't get less alpha. You know. Okay. That's why even in first year in thermal properties of matter, we say the length of conductor should be constant in pendulum clocks. If the length changes, time period of pendulum clocks change. That's why length should be constant in all seasons. So we prepare the pendulum clocks with what kind of element, Nana? You know it in your first year. Pendulum clocks are made with, anyone remember the name? Invar steel. Am I right? Invar steel. It is an alloy. That's what I'm saying. And my intention is direct conductors won't produce such kind of effects. Alloy is only more effective. That's why alloys are very efficient compared to direct conductors. Okay. So same kind of one alloy here we are using to get very less alpha. Okay. So for them, I am using here an alloy that is constant. Okay, one alloy or another alloy, manganine. Okay, which nine? Manganine. So constant or manganine, these are used to prepare the lab resistors. And this is one objective point, theoretically, like a statement type of questions. Okay, the lab resistors are made with constant and are manganine. Yes, statement 1 is correct. Statement 2, because their alpha is very small, close to 0. Yes, statement 2 is also correct. So final option, statement 1 is the correct, sorry, statement 2 is the correct explanation to statement 1. Okay, this is 1, but it is constant or manganese, both are conductors only, Nana. Their alpha is positive, not negative, positive and very low. Okay, practically 0 is impossible, Nana. 0 and ideal. Okay, so ideal case we are not discussing. Apart from 0, very low, how much? Almost like a 0.08 into 10 to the power of minus 4. Very small, like. Next. Lab resistors. Ante their resistance is constant. For moderate changes of temperature. At high temperatures, no one can stop in increasing the resistance. Nana then evvadu stop cheyaledu. Okay, so we can't. But at moderate temperatures means while doing the experiments in the lab, the temperatures won't be increased very high. Okay, so just moderate changes of temperatures we see. That time the resistance should be constant in the lab. So we prepare the lab resistors with constant and or magnet. Okay, number one. Number two, sometimes we require heating elements. Okay, so heating elements. Yes, this is correct only. The heating elements should possess data spelling from should have. Okay, what came down on a heating elements means quickly they have to produce the heat and their resistance should be increased quickly. Their resistance should be increased quickly means their alpha should be high, should have high alpha. What came small alpha, we came high alpha. Again positive only, not negative. Mari high alpha ante what kind of materials produce high alpha, sir? Which material has high alpha? Again, direct material won't have high alpha. Okay, so malli ever sir alloy, ever sir, ever can idea on an ID? Nichrome, that is nichrome. Okay, has high alpha, thus they are used to, it is used, better way, right? Yeah, it is used to prepare heating elements. అందుకే మనం we use nichrome spring నాన్న. అంటే ఎనీవన్ సపోజ్ అబ్జర్వ్డ్ ద ఎలక్ట్రిక్ స్టవ్, మరి ఎవరైనా చూసారో లేదో ఐ డోంట్ నో. If you see the electric stove, there you can find some spiral spring. Okay, a spiral spring, if you pass the current through it, then very lot amount of heat in very short span of time you will find. Okay, ఈ nichrome springs they use even in burial ground also. Okay, burial ground లో nowadays electric ఇవి ఉన్నాయి కదా, నన్ను అబ్జర్వ్ చేశారా? They keep the dead body on some stand and they keep it in some like oven. ఒక ఓవెన్ ఎలక్ట్రిక్ ఓవెన్ లో పెట్టేస్తారు. ఇమ్మీడియట్లీ యూ విల్ గెట్ ద యాష్ ఈవెన్ ఫ్రమ్ బోన్స్ నుంచి కూడా మనకి యాష్ వచ్చేస్తుంది. ఓకే, అంటే వెరీ లాట్ అమౌంట్ ఆఫ్ హీట్ విల్ బి జనరేటెడ్, రైట్? అంటే ఎలక్ట్రిక్ ఓవెన్స్ అంటాం వాటిని. దేర్ యూ యూస్ దీస్ నిక్రోమ్ స్ప్రింగ్స్ ఎందుకంటే దే ప్రొడ్యూస్ లాట్ ఆఫ్ హీట్. కానీ దెర్ ఈస్ వన్ డిసడ్వాంటేజ్ నాన్న. మరి అంత అమౌంట్ ఆఫ్ హీట్ ప్రొడ్యూస్ చేస్తే why don't we use these nichrome springs in geysers and immersion heaters? Reason behind, nichrome is a very good conductor of electricity. It is conductor, nichrome is a conductor. Okay, problem is if you immerse in water, the water also will be electrified. Okay, and that's why when it is turned on and whether the water is hot or not, to check if you put your finger there, you will get electric shock. This is the disadvantage. Anduku in immersion heaters and in geysers, they won't use nichrome. Okay, nichrome use cheste nanna. Suppose if you purchase one nichrome spring and put it in water as immersion heater, okay, in short span, nearly in 30 seconds, not even 1 minute, 30 seconds, the water will be raised, means the temperature will be raised to nearly 70 degrees Celsius. అంటే ఇద్దరు స్నానం చేయొచ్చు ఒక్కడు కాదు విత్ దట్ వాటర్. Are you there, Nana? All of you? Are you there? Okay, right. Because of power loss, I lost the connection, Nana. No problem. So finally, that what I try to say, what when the temperature is increased, the resistance of nichrome spring will also be increased. Okay, right. I think this is the last page what we try to discuss. No, I think I will show the last page. Yeah, this is the last page. Here we are, am I right? Okay. Yes. So finally, here we found nichrome is a good conductor. The final point here, what I am saying. Okay, we are going to close the call here with this point. Finally, I am saying nichrome is a good conductor. That's why they are not used in the geysers. Okay, and immersion heaters. Idi nanna. So today we completed up to how the temperature changes the resistance. Okay, is it clear? Right, Nana? So shall I close the call here?